Okay, I am going to make a rather long video here that's going to walk us through how to do the problem set. Okay, so let me get all set up here, which you would have thought I'd do before I'd start the video, but I did not. So, give me a moment here. Okay. So I'm gonna I can't, I'm going to do this in Word. I'm going to be drawing the things out. So I'm going to presume that you've got the file open that has the problem set on it. And basically what I want you to do, or what I'm going to do, is walk you through each of the problems, what the strategy would be and whatnot. It'd be your responsibility basically to write it up. I'm sure inevitably in the speed in which I'm making this, I'm going to be making mistakes. So that would be on you to find my mistakes and whatnot. Okay, so let's start. So in number one, we're told a chair manufacturer has an assembly line where the wage is 30 bucks an hour and that the rental cost of the machinery is $15 an hour. We are told that the chair can be produced using 4 hours of labor or machinery in any combination. Now, it turns out that that in any combination portion there is actually pretty important. Um, so basically, what that means for us here is that as we start to graph this out, right, and we know we're going to be looking for a picture like this, right? What we know is that typically the picture looks like this. But, and this becomes important here, but in this case, the isocont is now going to be constant because what I told you was that the marginal productivity of labor equals 0.25 of a chair, and that the marginal productivity of capital is 0.25 chairs, and that it's not changing, right? Any combination, 4 hours of work, 4 hours of rental of capital equals one chair. So, right, so marginal productivity of labor would just be a quarter of that. So what that means is that in terms of the marginal rate of technical substitution, which would be MPL over MPK, would be -1. But that this, right, is here. So we hit a button here now. I don't know how to stick it from this. Sorry, I don't know how to stop. There we go. Okay, so now we've got an issue. We've got -2 as the slope of my iso cost, -1 as the slope of my iso quant, which then means for us here that even though the typical picture is right here, the one you're familiar with, that instead what we've got here is an iso cost that looks like this. We've got an iso quant that looks like that, right, which is flatter, -1 versus -2. And what we see is in that pretty extreme example, is that we probably most likely have a corner solution here, but it also means that there's no circumstances where they're going to hire any workers because if they're equally productive, why wouldn't they just hire the capital, which is cheaper because it only costs 15? And so use all that information then basically to finish up the rest of number one. And let's move on to number two. Okay, suppose the economy takes a downturn. Show that the economy takes a downturn, labor costs fall by 50% and are expected to stay level. Show graphically how this change in the relative price of labor and capital affects the firm's expansion path. So again, we'd have something like this: quantity of labor, quantity of capital. The typical optimal solution would look something like that. And again, we were told that the labor costs are falling by 50%. So that means that my ISO cost is going to become flatter. And essentially what that would mean for us, right, is that if we drew this new ISO cost, or sorry, ISO quant, right, is that what we're going to see is that after the wage fall, let's put this in a different color. So what I'm drawing here in the purple would be, what if the wage reduction hadn't occurred? Then we'd see something like this for the expansion path, right? Because these two lines would be theoretically parallel to each other. But instead, what we're seeing here, again, this isn't going to look perfect, but instead, what we see is that the expansion path, which is the line I'm drawing out here, that the expansion path after the wage reduction has gone down, has become flatter. And so that's kind of essentially what you'll be drawing out for number two. Again, maybe elaborate some more, add some words and whatnot. Okay, let's look at number three here. How do I add a new page if I just keep drawing? Okay, I'm going to pause the video here so I can figure out how to add a new page. Okay, well, I backwards figured it out. So let's not worry about it. Okay, let's start this. Number three. So I've q which looks like Q equals 10K to the Q equals 10K to the 0.5 L to the 0.5 for company disk, and that for company floppy. And what we're asked is if both companies use the same amount of capital and labor, which will generate more output. And then in letter B, assume that the capital is limited to 9 machine hours, but labor is unlimited supply. Where would the marginal product of labor be greater? Okay, so now in solving this, what we need to do here is start to think about what the different options would be. Um, Essentially, what we would see is that if they use the same amount of capital and labor, but if we were to see that the amount of capital didn't equal the amount of labor, then they're not going to produce the same amount of output. How do we know that? Well, because each of these inputs have a differing level of productivity, right? So you could have 3 units of capital and labor, right? And if you had 3 units of capital and labor, um, right, you're not going to really be able to um, tell very much because, right, it'd just be 3 to the 0.6, 3 to the 0.4, which is going to still equal 3 to the 0.5, 3 to the 0.5, right? Because the exponents add up to 1. Where you're going to get the difference is that, let's say they have the same amount of labor, let's say with the 3, but let's say they now have 4 units of capital. Now firm 2, floppy, is going to end up being more productive because capital, if it's greater than the labor, that's going to really help floppy because it actually turns out to be more productive with capital. So again, you're going to have to write this up, but here's my scenario I'm saying. That if you gave each firm the same amount of labor and capital, then it'd be 3 to the 0.6, 3 to the 0.4, 3 to the 0.5, 3 to the 0.5. You're going to get the exact same answer in terms of the production. So there's going to be no way to kind of tell what's going on here. Where you're going to see the difference is that they each have 3 units of labor, but they have a little bit more capital. And if they have that little bit more capital, because the marginal productivity of capital is greater for floppy, then that firm is going to be able to produce more. Now, that gets us through A. What about B? Well, if the capital is equal to 9, then what happens to the production functions? Then for company disk, right, it would just be 9 to the 0.5 power, right? So the square root of 9, which is 3, 10 times 3 is 30. And that for floppy, now it would be 9 to the 0.6 power times 10, which gets us, calculator. Okay. And so then what you can do to kind of solve this out here is create for yourself a little chart. And what I want you to solve for here oh, sorry. Marginal productivity of labor per disk. Quantity per floppy. And so basically what you're going to do here, right, when it's 0, these would be 0. But then basically what I want you to do is put 1 in for this, solve it, find out how much the quantity changed. That's going to be your answer here, right? Then put in 2, and then your quantity will have increased. That difference in the quantities, that's going to be your MPL here. Then repeat the same for floppy, same process. What I'm hoping that you're going to find, at least what I found, is that the marginal productivity of labor is greater for disk. Confirm that by filling out the rest of this chart. Okay, let's talk about number 4. Okay, so now we've got the input prices. We've got wages equal to 3, R equal to 2, Q equaling 10 KL. And what we're asked to solve for here is what is the least cost combination for 60 units of output, and then how are those inputs going to change when we're talking about 240. Well, to do this, I need to find the MPL and I need to find the MPK. The MPL is going to be 10K. The MPK, which would be the first order partial derivative of this, is going to be 10L. The marginal rate of technical substitution is going to equal 10K over 10L, which is essentially K over L. K over L is going to equal 3 over 2. 2K is going to equal 3L. K is going to equal 1.5 labor. What you're going to need to do then, well, sorry, I have to pause this because I have to add a new page. So 1 second. Okay, I think I'm getting the hang of this. So now what I need to do sorry, I don't know how to get rid of that blue box. Sorry. Oh shit, look at all that. Why is it doing that? Oh, I got it to work. Okay, so now I'm going to do 60 equaling 10 times 1.5 L times L, right? Because I'm going to substitute for the unknown so that I can now just solve for L. That would give me 60 equaling 15 L squared. Divide each side by 15. That's going to get me 4 equals L squared. Take the square root of both sides. And that's going to get me 2. Where K equals 1.5 times L. That's going to equal 3. And so there we go. To produce 60 units of output, I would have 2 units of labor, 3 units of capital. I won't solve it for you, but basically repeat that process for having 240 units. You don't need to resolve this optimal ratio. That optimal ratio will be true regardless of the output level. So just resolve this now for 240. Yeah, I'll make you do a little bit of the dirty work here. Okay, now I'm making light bulbs. Okay, first question is, what is the marginal productivity of labor and of glass? So now we're not using capital, but it would just be the other input. So the marginal productivity of labor would just be 10G, right? Because presumed 1, presumed to 1, 1 to front, L to 0 would be nothing. MPG would equal 10L. That would mean that my marginal rate of technical substitution is 10G over 10L, which is simply just G over L. And that answers part A. And then for B, here we would be drawing a isoquant map, and we're told that the cost of labor is 4, and that the cost of glass is 4, and that 90 units are produced. So it would look something like this. And what we need to solve for to fill out the rest of this here is 90 equaling 10 LL, because the G over L is going to equal 4 over 4, so 4G equals 4L. G equals L. Right, I just set this equal to the cost of the two things. So this would be 10L squared equals 90. L squared equals 9. So L equals 3. So then, okay, so we know L equals 3. And as a consequence, G must also equal 3. So this would be 3 and 3. There we go. We've drawn our picture. Then in letter C, we're told that the quantity is going to increase to 160, and we're asked if this firm is going to have constant increasing or decreasing returns to scale. Well, to determine what the returns to scale are here, actually all that we do is we add up the exponents. Remember, there's a presumed 1 and a 1. When it's equal to 1, the exponents, adding them up, we have constant returns to scale. If it's less than 1, we have decreasing returns to scale. And if it's greater than 1, we have increasing returns to scale. Well, 1 plus 1 is greater than 1. So we do have increasing returns to scale. Okay. Okay. Number 6. Here we have a short-run cost function. Where its total cost equals 200 plus 55Q. And I'll just ask you a series of 4 questions about the cost from these things. So in letter A, we're asked what the fixed cost is. Well, that would just be the constant function here. So it is the 200. In letter B, we're asked if the company produced 100,000 units, what would be the average variable cost? Well, it's going to be determined for us by 55Q. So it would be 55 times 100,000. That's going to get me at least my total variable cost, right? So that's going to be so that's going to be our total variable cost. And so what we're going to see here, right, Um, sorry. 55 million. But then the average variable cost, which is what's asked here, would be the 55 million divided by 55,000, or sorry, by 100,000, because right, it's going to be the total variable cost divided by the quantity. And what's the answer going to be? That same 55,000, which you could have just gotten by the constant term in front of the variable. But I just kind of wanted to walk you through the other math here. Then in letter C, we're asked what the marginal cost per unit produced is. Well, that would say how much does the total cost change when quantity goes up by 1? Be 55. And then finally in letter D, what is the average fixed cost? Well, we don't actually have a number here, right? So average fixed cost would equal fixed cost divided by quantity. So in this case, it's just going to be 200 divided by Q. Okay, let's look at number 7. So in number 7, we are managing a plant that's producing engines, and we're given the production function Q equals 5KL. We are told that the rental rate is $10,000 per week. In terms of the labor team, we're told that that is 5,000 a week. And then we have costs, raw costs. Let's just call it variable costs here. Variable costs equal $2,000 per machine. And we are told that the capital is fixed at 5. Okay, so that's all the information at least. In letter A, we're asked what is the cost function for our plant. So in terms of our cost function, sorry, not Q, total costs here would equal what? 10,000 times the 5, right? Because we know that that's how much capital we have. 5,000 times the number of workers, which we don't know, so it's just going to be L, plus 2,000 times the number of engines built. That would be our variable cost there. Now, the problem here would be we have two unknowns. We have L as an unknown, and we have Q. So we need to get rid of an unknown. The question would be is, how do we get rid of it? Well, we need to find the MPL and the MPK. What we know is that our production function is given by 5KL. So that would mean that our MPL right is 5K. that our MPK is 5L. And what we know, right, is that if the Q equals 5KL, and we're told that the K is equal to 5 because it's fixed, then Q is going to equal 25L, or that L is going to equal Q divided by 25. How's that going to be useful for me? Because now what I can do is substitute. And sorry, 1 second. Yeah, okay. So now I'm going to have 50,000 plus 2200 Q. So this turns out to be 200 Q. So plus 2000 Q gives me 2200 Q. That's going to be my total cost function, right? So just do the 25, that would be 200, right? 50 and 25, so this would be 2. So 200 Q plus 2000 Q gives me 2200 Q plus 50,000. There, I have answered part A. Well, actually part of it, because now I need to find the average and the marginal costs. And I'm running out of space. So that would just give me average cost of 2200 plus 50,000 divided by Q as my average cost. Sorry, when I do the page break, it puts it above, so now I'm gonna have to scroll up here. Page is gonna be right here. Sorry, just trying to get this to work. And that my marginal cost would be my change in total cost over my change in quantity, which is what? The 2200, right? The thing that changed with respect to Q. And so then to answer the last part of this, how do the average costs vary with output? Well, what would happen would simply is that as quantity goes up, the average costs are going to be falling. Um, primarily because, right, in terms of the overall curve, um, uh, the marginal costs are going up by 2,200, but the total costs are um, uh, decreasing at an increasing rate. Okay, now in terms of letter B, for number 7, we're told that the quantity is 250, and we're asked what is the average costs per engine. And how many teams are going to be required to produce these 250 engines. Well, to do that, um, to produce 250 engines, what we're going to need um, is that if we have 5 assembly machines, that would mean we have to have 5 teams, right? Because we'd have one team at each assembly machine. So that would mean for us here is that each team, as we split them up, each team is going to have one machine and 2 workers. So what that gives us here is that still using our Q equals 5KL, right? Is that KL equals 50. But again, sorry, if our number of if our amount of output is 250 and L is still equal to the Q over 25, then what that's going to mean for us here is that we have 10 workers split over those 5 teams. That gets us 2 workers, 1 machine per team. And in terms of the average costs, that would be my 50,000 plus my 2,200 times 250 divided by 250. And I already solved this. And I got 2,400. And then in letter C, we're asked if they've got are they being cost efficient? Well, what do we know would be true if they were being cost efficient? If they were being cost efficient, then this would be true. It would just be 1 over 1. Well, what do we know in terms of the cost? That ratio is 1/2, 5,000 over 10,000. What do we see? Not optimal. Okay. Let me pause and then I'll start a new page. Okay, number 8. We've got the tortilla, perfectly competitive market. We've got a supply curve. 1, 2, 3, 4, 5. And I give you an inverse demand curve. So I made your life a little easier there. And they tell you that the marginal cost is as follows. And we're asked to, in this perfectly competitive market, first find the equilibrium price for tortillas. So in a perfectly competitive market, we're going to set the MR equal to the MC. And in this kind of market, marginal revenue is going to be the same as the inverse demand function. So that means I'm going to have 11 minus 0.00002 Q, which is my marginal revenue, equaling 0.1 plus 0.0009 Q. Sorry, we're actually doing this. Sorry, sorry, this is B. Sorry, this is not A. Sorry, I'm actually solving B for some reason first. Okay, I'm actually confusing the two parts here. Let me do this again here. Okay, so what we need to find here is that in the overall market, we want to find this, right? We want to find that point, which for us in our case here is going to be the 0.00001, 2, why did I make so many zeros? 4, 5, 2, Q equaling 11 minus 0.00002 Q. Well, divide each side by 0.00002. Oh, no, actually, I'll make your life easier here, sorry. Add 0.00002 Q to each side. That's going to get me now divide each side by 0.00002. And it's going to get me a Q of 500,000. Okay, so now in this market here, I now know that this is 500,000. Now I can substitute that back into the function where P equals 11 minus 0.00002 times 500,000. And we're going to see here is that P equals 1. Okay, so that gets us through A. Then in the letter B, now we would have our MR equal to MC. But now, since I already know my marginal revenue, that it's 1, I can now just set that equal, I can just set that equal to my marginal costs, which is 0.1 plus 0.009. And solving for that, we know that each individual firm is going to be charging the $1 market price, but that the quantity will be 1,000. So basically what we have found here, combining A and B together, right, is that for this perfectly competitive firm, the price would be $1. And that with a marginal cost looking like that, that each of these firms would make 1,000 units. Now, letter C is actually pretty easy once you've gotten through A and B, because now what we know is that if we had 500,000 total quantity with each firm making 1,000, then we know that we would just have 500 firms, right? Divide your market quantity by your firm quantity. Okay. Now number 9. In number 9, we've got the market for mountain spring water. And I give you that demand function for the market. And the marginal cost is 0 because I say that the mountain spring water can be produced at no cost. And the question then is, how much will the single price monopolist produce? And then what would be the price and the output if it was perfectly competitive? So now we get a good comparison of how you solve these. So let's do A. We know we're going to be setting marginal revenue equal to marginal cost. For a single price monopolist, the marginal revenue is going to be twice as steep as the inverse demand. So my marginal cost. My marginal cost will be 600, sorry, my quantity will be 600. And in terms of my price, going back up to my function here, 1200 minus Q. So there we go. We've got the single price monopolist all set up. Now, the question would be, what does this look like if the firm is perfectly competitive? if they are perfectly competitive, and we still have this as my inverse demand, then we know that the marginal revenue is going to be the same. So now it's going to be 1200 minus Q for MR equals MC. Is going to be 1200 minus Q equaling 0, the marginal cost. Meaning that my Q is going to be equal to 1200. And my price will be 0. And that gets us then to number 10. Okay, let me pause here because I'm going to start a new page. Okay, so now for number 10, now we've got two different markets. And in these two different markets, the East Coast and the Midwest, in each of these markets, they act like a monopolist. So first we're asked, what will be their price output, profits, marginal revenue, deadweight loss if they do price discriminate, and what if they can't price discriminate? So what does that mean for us then? So if they can price discriminate, with these two different markets, then the marginal cost in each of these markets, the marginal cost is going to equal 3, right? Because that would be the marginal cost is given us as 5 plus 3 Q1 plus Q2. So it's just going to be that 3, right? Because that's our variable function. But in terms of the marginal revenue, in market 1, in market 2, which then setting equal in each market, MR equals MC. Right, because each of these marginal revenues, because this is a price discriminating firm, single price monopolist in each market, then their marginal revenue is twice as steep as their inverse demand. And okay. And we can find the price by 15 minus Q1. Goes over here. In market 2, the price would equal 14. And then you're asked in the same question, so we found the price and the output. Now you would also need to find the profits, the marginal revenue, um, and the deadweight loss. Um, you know what? Don't worry about the deadweight loss. I know for certain I'm not going to have you solving that um, on the exam. So don't worry about it. But let's go over very quickly how to solve the marginal revenue and the marginal costs, or sorry, the total profits and the total revenue, the total costs, and the profit. Well, in each of these markets, right, we're just going to take the 6 times the 9. And the and the total costs. So total revenue is going to get me 91.5. For my profit. Again, let's not worry about the deadweight loss. But what if then in part 2 of this, what if the law prohibits charging different prices in the 2 regions? So what would happen if they were forced to act like a single price monopolist? Well, what that would mean for us then is that in terms of the demand, right, we're just going to add up our individual demand functions. So what are we going to have here? If it was forced to act like a single price monopolist, we'd be at 40 minus 6q. Marginal cost would still equal 3. And it's just rounded to 21.5. And so, right, then you could repeat this to find the total revenue and then find the total costs. Okay, took an hour. You're probably going to pour over it for a bit longer than what I just did. Again, I'm not trying to make this sound like a super easy project or anything like that. This is just me kind of solving it right in front of you. And again, I probably most undoubtedly made some mistakes just kind of roughly sketching this out. So if you want to look at it, tell me in class what errors I've made where, or if you have questions about the math I did. But again, don't worry about the dead weight loss here in number 10. I know I'm not having you do it on the exam, so don't worry too much about that. Okay.